So in Chemistry 1, what we've been doing here at the end of this unit is we've been focusing on models that help us describe how atoms bond together into molecules. So you've learned a few different theories. You've learned VSEPR, which helps describe shape, but it was a little bit weak in how that in the VSEPR theory, you kind of had double, single, triple bonds, lone pairs, as if but they somehow were acting all equivalent. And that doesn't really make sense, that these sorts of orbitals wouldn't necessarily act equivalently. So we moved to valence bond theory, which allowed you to come up with this concept of hybrid orbitals, which says in a molecule, the orbitals that came from the individual atoms, the S, P, D, and Fs that you understood, came from the individual atoms, they somehow hybridize so that in the molecules, they actually give equivalent orbitals. So we learned about sp and sp2 and sp3 and even sp3d and sp3d2 hybrid orbitals, which better described equivalent molecular orbitals. So today what we're going to do is work on our last theory. It's called molecular orbital theory. It has very little assistance with helping us see geometry. So it may not be used to explain the geometry around an atom, but what it's helpful for is electronic transitions like we see in spectroscopy, which we would have seen in the lab, but we kind of got knocked out of lab due to bad weather, but maybe we'll get a chance to get back in there. But at some point, if you continue on to Chemistry 2, you'll definitely look at spectroscopy, and we did a little bit right at the beginning of the semester, where you're able to stimulate a metal and it would have an electronic transition based on its molecular orbitals. So we're going to look at a theory that would better explain these kind of transitions that are allowed. Another thing it lends to is it helps you understand and more accurately predict bond order. And from bond order, you can then directly predict strength and length. Just kind of as we talked about in class, that we said, hey, a bond order of 1 is the same thing as our model of a single bond. A bond order of 2 is the same thing as our model as a double bond. A bond order of 1.5 would therefore be somewhere between the single and double bond as far as length and strength. So we're going to use this theory, and then again, the application for you in Chemistry 111 is that you'll be able to determine bond order, and based on bond order, you can make some predictions. And it also has implications for paramagnetism, because if you look in the molecular orbital theory and you see unpaired electrons, then that molecule should be paramagnetic or exhibit a magnetic field. So let's get started so we understand that, how it works. It's very simple. It's also used for electrochemistry, like how you promote electrons to create electricity or for doing batteries. The combination of orbitals that form bond is viewed as a combination of wave functions. So there's two ways to think about how this molecular orbital theory comes apart. The first one we just kind of introduce you to. It'll probably make some better sense as you've taken more physics, but it probably isn't really that helpful to understanding even the models we'll work on in Chemistry 111. But we think about bonds being formed as kind of like electronic waves. And then the other one we'll look at is we'll get more to a physical model where you can actually see orbital shells, almost like when we did electron filling theory. So anyway, what we're going to work on is the idea that if you have any atomic orbitals that come from two atoms, they'll come together and make a molecular orbital. Now what we're going to do is we're going to do homogeneous molecular orbitals just to introduce this to you in Chemistry 111. And so in other words, we're not going to bond a carbon to an oxygen. We're going to bond a carbon to another carbon, or an oxygen to another oxygen, or a lithium to another lithium. We're really only going to work on those sorts of molecules for this model so you can understand and be introduced to the model. So what we understand in this theory is something called an anti-bonding molecular orbital. In other words, it's an orbital that exists. It's like we've talked about this quantum shell that's there. It exists in space. You can promote electrons into it, but it isn't necessarily, doesn't always have electrons in there. It's just there in space. And then if you produce enough electricity to get into that shell, you might see electrons promote up there and then fall back down, emitting light, etc. So we're going to kind of get this from a wave concept. If you had two waves, so look at these waves that I'm kind of going over with my cursor, and we're saying, hey, these two waves are in phase. In other words, what they do is think about two water waves that come in together and hit each other, and they're both, crests. Then you could imagine that that wave would get twice as high. But on the other hand, you might have waves that are out of phase. In other words, a crest hits a trough, and at the moment that those waves hit, then the waves cancel. So here's what we see in terms of that. I have this top left picture where it shows two waves that are in phase, and you can see parts of the wave come together right where this wave face is hitting the other wave face. Those two are in phase, so they reinforce. So if each one had an amplitude of, say, 0.5, then together, when they combine, they would have an amplitude of 1. Now, on the other hand, if the waves were out of phase, where this wave on the left is coming in as a crest, and the wave on the left is coming in as a trough, at the moment that they combine, where one has a positive 0.5 and one has a negative 0.5, at the moment those combine, they literally cancel, and that's what we call an anti, right? This would be an anti-orbital. In other words, it's not helpful to bonding at all. It doesn't give any strength. So it's kind of a wave explanation of this, which is, in my mind, a little hard to understand. It's not that helpful to students. This way of thinking about it makes a little better sense to me. So let's just say we have two hydrogen atoms, and we say they're going to covalently bond. So if we say they're in phase, the idea is what we've talked about in class. The protons have a kind of a sigma type bond where the electrons are centered between the two protons, and then the proton on the left is able to reach out and share the electrons that are centered between the two atoms, and the proton on the right is able to reach out and grab the electrons that are centered between. These are in phase, and they are a bonding molecular orbital. And in fact, we use this sigma to remind us that, yeah, the electrons are centered. This picture doesn't show it real centered, but the electrons are centered between the two nuclei, and that came from the 1s suborbital. So that would be an in-phase wave. Now, on the other hand, if the wave, at the time that the hydrogens came together, let's say the electrons were away from the proton. Remember, it's a sphere around the proton. So at the moment that the electrons come up, let's just say that this particular one on the left had the electrons on the back side of the sphere, and this one on the right also had the electron on the back side of the sphere. Well, as these two hydrogen atoms came together, you would be bringing a positive piece of the atom close to a positive piece, and you go, that doesn't want to bond because opposites actually, or like charges, repel. So therefore, you'd have an anti-bonding molecular orbital. And what does that mean? It means that if you wanted to get these two atoms together, you'd have to put energy into them to force them together, because you're basically putting two positive charges close to each other. And so if you look at the energy diagram, to put those together when they're out of phase like this, you would literally have to pump energy in order to see that bond. Whereas on these, because it's favorable, the positive is grabbing the negative, that's a favorable situation, it will release energy when the bonds form. And this is the common thing we know, as we've talked about in class, that when you form a bond, it's exothermic, it releases energy. Okay, so with this kind of model in mind, you go, okay, so anytime I have two atoms, basically I have two electrons coming together, then I'm going to have a anti-bonding molecular orbital, and that's the one up high, and we have a bonding molecular orbital. That's the one that's low energy and favorable. So kind of the interpretation is this: for every atomic orbital. You know, I bring in one s, it bonds to the one s of the other hydrogen, so that brings in two suborbitals. That would mean I have two molecular orbitals, and one of those will be bonding, that's the one down here, and one will be anti-bonding. It's just that simple. So remember, anti-bonding is out of phase, and then bonding is in phase. Bonding is attractive. It gives a solid bond, or a bond order. In this case, it would be a bond order of 1. Anti-bonding is takes away from bonding, so it lowers the bond order. So bond order is always calculated this way. Whenever we build our molecular orbital diagram, you take the number of electrons in the bonding molecular orbital, you subtract it from the number of electrons in an anti-bonding molecular orbital, you cut it in half, and you'll now have the bond order. So in other words, if I had 4 electrons in the bonding molecular orbital and 2 in the anti-bonding molecular orbital, I'd go 4 minus 2, that leaves 2, cut it in half, that would be a bond order of 1. That would represent a single bond. It would rotate, it would be the length of a single bond, and it would have the strength of a single bond. Bond order 1. Okay, so again, I just remind you how this happens. Molecular diagram shows the atomic orbitals. Now, when you do the diagram, you usually show the atomic orbitals that form the molecular orbital, but that's just for bookkeeping, okay? And for every atomic orbital, there is a molecular orbital. Now, remember, the way you can think about this is we're bonding two things, so we're going to always have an even number of atomic orbitals. Two s's come together, I'm going to have two s's, so that's going to split one into bonding, one into anti-bonding. If I brought in one s and 3 p's, that's going to be, okay, I've got 4 atomic orbitals from each atom. That's going to be a total of 8, so that's going to split 4 into the bonding area and 4 into anti-bonding area. Okay, and so then the molecular orbital diagram is the one in the middle. You fill it just as you did in Hund's rule. So here's an example. So here's the H2. I'm going to show you how to do this with molecular orbital diagramming. So the first thing you do is you build the molecular orbitals, start with the atomic orbitals. So each hydrogen brings in a 1s. So here's and again, you just focus on valence electrons. You can build molecular orbitals with all the electrons, but basically what you'll end up with is a lot of wasted paper, because the core electrons always cancel, and they don't count on the bond order. So the bond order is only determined by valence electrons. So long story short, you're building molecular orbital diagrams out of valence electrons. So when you talk about hydrogen, comes in with 1 electron. That 1 electron is in the 1s. So this over here in the diagram is representing the atomic orbital that this hydrogen contributed, or 1 hydrogen contributed. And on the left-hand side is the atomic orbital, the 1s, a single electron, that the other H contributed. Now, these are just for note keeping on the right and on the left. In the center is the actual molecular orbital. So what do? We come in with 2 atomic orbitals. So we then make 2 molecular orbitals. 1 bonding, it's the low energy one, and 1 anti-bonding. So that's as simple as it gets. If I bring in 2 atomic orbitals, I'm going to split into 2 molecular orbitals. If I brought in 4 atomic orbitals, I'd split into 4 molecular orbitals. And you always split it 50-50. Of the 4 that I create of the molecular orbitals, 2 go to bonding, 2 go to anti-bonding. So build molecular orbitals by taking the atomic orbitals, splitting them evenly between bonding and anti-bonding. Each hydrogen contributes 1s, which is 2 atomic orbitals. They split into 1 bonding, 1 anti-bonding. Then the last thing you do is you just count valence electrons and fill them, just like we learned to fill things in when we were doing electron shell filling. where you say, okay, I got 2 electrons. I'm starting at the low. Everything of equivalent energy fills up first. That's Hund's rule. You fill every individual molecular orbital that's the same energy with the spin up first, and then you go back through and pair it. And that's Pauli exclusion principle, that you pair it so it's spin up and spin down, and then continue on. And then basically when you're done, you can use that rule and say, here's our hydrogen, an H2 atom, and I've now filled it with my 2 electrons, one spin up, one spin down, and now I'm ready to figure out the bond order, right? So that's the last step. Fill with valence electrons using your filling rules. So I've got 2 electrons. I'm going to fill the bottom. This is a bonding orbital. It's got it has 2 electrons in it. And the one I star, by the way, is the anti-bonding. So basically the notation looks like this. These are sigma, meaning they have electron overlap in the center. They came from 1s's, so we call them sigma 1s molecular orbital. Now, when you see a sigma star, the minute you see the star, you call that an anti-bonding orbital. So I now have 1 bonding and 1 anti-bonding. I have 2 electrons. I fill them spin up, spin down. If I'm going to do my bond order, it's number of bonding, that's 2, minus the number of anti-bonding, that's 0. And then I split that in half. That makes a bond order of 1. So we know that H2 makes a single bond. Bond length, single bond strength, single bond. Does it rotate? Yes, single bonds and below all rotate. And in this case, it's dimagnetic according to the diagram, because you have a spin up bound to a spin down. So electrons are placed in the molecular orbitals just as they are in atomic orbitals. They're filled with increasing energy. All molecular orbitals hold a maximum of 2 electrons, just like electron filling diagrams, just like we learned earlier. Orbitals of equal energy are half filled with spins parallel before pairing spins. That's, Hund's rule. And then pairing spins, where, in other words, now once you put 2 in the same orbital, they're spin up, spin down. That's Pauli exclusion principle. A molecular orbital configuration shows the type of the molecular orbital and the number of electrons each contains. So if I was to try and do a molecular orbital configuration, it's a sigma 1s with 2 electrons in it. This, again, is a fairly useless notation. This diagram is what you could interpret and make some sense out of. All right, so we're now going to move on and do something a little more complicated. So we're going to do helium. So again, remember, we're not going to do helium mixed with hydrogen or oxygen mixed with carbon. We're going to do single, atoms bound to themselves. So we're doing an He2+. So again, helium only has s suborbitals. So if I brought in the 2 suborbitals, the best I could do is I could do 1 spin up. One bonding and 1 anti-bonding. It'll look just like hydrogen 2. Then we count electrons, He2+, brought in a total of 3 electrons. So I start filling from the bottom up. And I go, okay, spin up, spin down. Then that next unpaired goes in the upper anti-bonding orbital. Then if I'm ready to do the bond order, I say bonding 2 minus anti-bonding 1 gives me a remainder of 1. If I cut that in half, then I have a bond order of 0.5 or 1/2. What does that mean? It's a little weaker than a single, it's a little longer than a single, and it's still able to rotate. Then if I go to helium, where there's not a helium plus, not a helium cation, but a helium 0, He2+, I now have 4 electrons to fill. So I fill 2 in the bonding molecular orbital, 2 in the upper anti-bonding molecular orbital. So then I go to do the bond order and I say bonding 2 minus anti-bonding 2 makes 0. Cut that in half, it's 0. It has a bond order of 0. There is no such a thing as a helium 2 atom or molecule, because there will not be a bond formed. That's the interpretation of a bond order of 0. Now again, I remind you, this 1s with the 2 electrons on the left and the 1s on the two electrons on the right, those are notes. They're saying where did these molecular orbitals came from? They came from 1s of a single helium bound to a 1s of another helium. These are just note keeping, and from those the molecular orbitals are the ones down the center. I could leave out the outsides and just fill if I knew the bond, the way to do the splitting diagram, which for everything with the single S, it's very simple. S makes one bonding, one anti-bonding. All right, so now we're going to try lithium 2. So now I'm going to try lithium 2. So lithium comes in with a single 2s. So once again, now we're out to the second level, and we're just focusing on valence electrons. It's in the hydrogen family, so each lithium brings in a single s electron. That's a total of 2 electrons. You split the atomic orbitals, one down to bonding, one up to anti-bonding. You fill with the 2 electrons, so you have a total of 2 bonding minus 0 anti-bonding, cut in half. That's a bond order of 1. So it's possible to have a lithium bound to lithium, bond order 1. You go to beryllium, second row, total of brings in a total of 4 electrons, 2 to the bonding, 2 to the anti-bonding. Same thing as helium. 2 minus 2 makes 0, cut it in half. It ends up being 0 bond order, which means there is no such a thing as a beryllium, a diatomic beryllium molecule, but there is such a thing as a diatomic lithium molecule. So it explains some of the metallic bonding of lithium. Beryllium, diatomic beryllium doesn't exist. Now, when you get into the molecular orbitals where you have p involved, where you have the p suborbitals involved, it gets a little more complicated, because as we saw in valence orbital theory, some of the pi or the p atomic orbitals are able to overlap end to end, and so that makes a sigma bond with some of the p suborbitals. So now this all looks, if you looked at it in terms of what does that look like, if you have 2 p's coming together end to end to where the electron density is centered between, it would look like a sigma, only it came from p suborbitals. And then if you had them where they were with the electrons to the outside and they were anti-bonding, it would look like these molecular orbitals. Whereas the actual true pi bonds, when they come together, as we've learned, between the 2 electron, the proton centers, the nuclei, the electrons are not centered, but they're out above and below in these pi bonds. And then the anti-bonding for the pi bonds would look like this. This would be the node, the anti-bonding. So this is the same model. Splitting diagrams for this look like when the 2 p's come together, they split differently depending on what, homogeneous diatomics you're working with. So for boron, carbon, nitrogen, look at your periodic table. Boron, carbon, nitrogen, look, that's the first part of the p suborbitals. It splits as you would expect. They each have 2 s's, so they do what we think, one bonding, one anti-bonding. But then when it comes to the p's, the way they split, the pi's go a little lower energy than the sigmas, and then that configuration where the 2 pi becomes the anti-bonding, or it just kind of, it doesn't really mirror, but it replicates above. And then when you look at everything, oxygen, fluorine, and nitrogen, the sigma from the 2 s's, they split very evenly. So notice over here, they didn't quite split as evenly. The anti-bonding is a little lower energy. There's quantum mechanic calculations behind that, so I can't explain even hand waving what the difference is there. The good news is that these splitting diagrams will be given to you, and these are all you're responsible for. So all you need to know is how to do, you can do your own splitting if it's S's involved, because you put one up and one down, one bonding, one antibonding. But for doing P's, then you're going to be given these splitting diagrams. So here we go. When you look at everything from the oxygen, fluorine, and neon families, it splits a little bit more like a mirror image, where you have the sigma bonding below the pi's, and then it just mirrors up where the pi antibonding is below, and then the sigma antibonding is the top. So what does that mean as you move forward? So here's the entire family. This is for making the diatomics: boron 2, carbon 2, nitrogen 2, oxygen 2, fluorine 2, and neon 2. And again, some of this is what we know naturally occurring diatomics, but some of these, like the carbon 2 and the boron 2, does such a thing exist? We can figure out with molecular orbital theory. And so for these, they have the splitting patterns done for you. So again, remember that the boron, carbon, nitrogen, they actually put the 2 down and the 1 up, the pi's down and the 1 sigma up. And then they just repeat for the antibonding, whereas the oxygen, fluorine, and neon, they look more like mirror images, where sigma's down, pi's are up, and then it just mirrors above for the antibonding. So anyway, basically you can look through these, and so let's just say we're going to do boron 2. So again, you'll be given the splitting diagram. You count electrons, so count over the valence electrons. That's 3 from each boron. That's a total of 6 electrons. You fill from the bottom up. 1, 2, 3, 4. Now that takes care of the sigma and the sigma antibonding. So those will actually cancel. That's one thing that's helpful if you're trying to do bond order. Anytime I fill my sigma and my sigma antibonding, you could just cancel those out, because that's 2 minus 2, cut it in half, that'll be gone. And then you could just focus on these are 2 bonding. So 2 bonding minus no antibonding, cut that in half, that makes a total of 1. So that would be a single bond in here, bond order of 1. Okay, it would be, according to this, it would be paramagnetic, yes, because it has 2 unpaired electrons. You go to C2. Now you're coming in with carbon having 4 valence electrons apiece, times 2 carbon atoms, that's 8 electrons. You fill from the bottom up. Basically, now we can just, these 2 cancel out. You can just focus on this and say, okay, here's my bonding. I've got 4 bonding, no antibonding, 4 divided by 2. That makes it a bond order of 2. So a carbon could bond to another carbon with a double bond. I said a single double, but an individual double bond. And that would be a bond order of 2. You look at an N2, and it is diatomic, and this will explain, it will bond as we see with our Lewis dot and our Vesper theory and our valence electron theory. These all correlate together. So if I did the total number of electrons, each nitrogen brings in 5. That's a total of 10. I fill from the bottom up. 2, 4, 6, 8, 10. Then when I go to do my count, I in essence have 6 bonding with no anti-bonding. Cut that in half, that makes 3. It's a triple bond. The triple bonds are all paired up, so that would actually be dimagnetic. And then here's the interesting one. So if you look at oxygen, and I'm going to go over and look at this differently. I'm going to, here's the splitting pattern for oxygen, right? So now let's go over here and look at this kind of individually. As you look at the other models we've used, you would basically, starting with Lewis dot, and then if you went to Vesper, you would go, okay, this oxygen, it's 1, 2, 3, it's sp2 hybridized. You have a sigma bond and a single pi. Everything's paired up. You go, wow, this thing is not magnetic at all, right? So, all your theories up to this point would say this thing is dimagnetic. But then you go to your molecular orbital theory and you go, okay, I have each oxygen brings in a total of 6 valence electrons. So we got how many to fill? We got 12. So we go 2, 4, 6, 8, 10, and then the last 2 go into the pi star, which means the pi anti-bonding, and because of Hund's rule, they're both spin up. So that would imply, first off, that it's paramagnetic because I have 2 unpaired electrons. So that's important. Then the second thing would be the bond order. We go, okay, I've got 4 minus 2. That gives me a total of 2. And then if I cut that in half, let's see if I got that right. Oh, sorry, I missed that. Okay, these 2 are taken care of, but I have 6 minus 2. I've got 6 bonding molecular orbitals, and I've got 2 electrons in anti-bonding, so I go 6 minus 2. That gives a total of 4. I cut that in half. That gives a double bond, which would bear out in my Lewis dot structure. So all of that works. The only difference is molecular orbital theory would say, yes, it's a double bond, the length and strength, it shouldn't rotate. All of that is borne out in valence bond theory. But the other thing that it would imply that valence bond theory or my Lewis dots don't indicate is that it's paramagnetic because I have 2 unpaired electrons, and I actually have a picture of liquid oxygen being dropped between 2 magnets or a magnet, and it basically suspends right between the magnets, which is evidence that it does have a magnetic field. So molecular orbital theory is the one that would have caught this and said, you know, you could indeed move liquid oxygen around with a magnetic field. So this will give you a chance to do a lot of practice. Now again, I just want to reinforce something. If you're given something with just single s atomic orbitals, something from the hydrogen family, something from the helium, right? Not the family, but helium, but something from the hydrogen family, something from the lithium family, those are only involving s, then I expect that you could create the molecular orbitals. On the other hand, if it's something from nitrogen, oxygen, well, to work out the whole set, anything from boron, carbon, nitrogen, oxygen, or fluorine, or the noble gas family, those involve p suborbitals, so you'll be given these 2 splitting diagrams. And again, they're going to be, you know, homogeneous diatomics, so B2, C2, or N2, O2, F2, or neon 2. So now if we're going to work these out, again, what you do is you just count your valence electrons. Nitrogen comes in with 5 and 5, that's 10, right? Then you fill, picking the appropriate molecular orbital diagram. This is not for the nitrogen family. This is for the nitrogen family. I'm going to fill from the bottom up. 1, 2, 3, 4. These are taken care of, right? Because bonding minus anti-bonding, cut in half, that's going to just zero out. If you have 2 and 2 minus, 2 minus 2 is 0. You cut it in half, that's going to cancel out. So all I have to deal with is how many are in this upper set. So I've got 10. So 2, 4. I go 1, 2, 3, 4. And then my last 6 go right up here in this set. And that's going to be 6 bonding, no anti-bonding. Divided by 2 is 3. Bond order is 3. Now, if I had an N2 molecule, that means I lost 1 electron. That makes it a 9. And if I stuck my 9 in here, I go 2, 4. My remaining 5 go up here. 1, 2, 3, 4, 5. I would have 5 bonding minus no antibonding. Cut in half would be a bond order of 2.5, which makes it a little weaker than the N2 molecule. I go to O2. That's a total of 6 times 2 is 12 valence electrons. I look at this is the wrong splitting order now. I go to this other diagram. This will be given to you. I've got 12 electrons. 1, 2, 3, 4 in the bottom. The remaining 8 go up the top. I got 1, 2, 3, 4, 5, 6, 7, 8. So I've got 6 bonding minus 2 anti-bonding. That's 4 cut in half. That makes a bond order of 2. When I go to O2, I've lost 1 electron. That's 11 electrons. 2, 4, 5, 6, 7, 8, 9, 10, 11. So I would have a total of 6 bonding minus 1 anti-bonding. That would be 5. You cut that in half, it's a bond order of 2.5. So now, according to this, I can now interpret on the chart. Okay, I've now created this little chart that says here's the bond order. And so pick the highest and lowest bond energies. So the high bond energy is the strongest bond, which is the triple, followed by nitrogen N2 plus cation and the O2 plus cation being very equivalent, followed by O2 being the weakest. That's in terms of bond energy. And then what two species are most likely to have a similar bond length? N2 cation and O2 cation. And now when I actually get the data from a table that says, okay, we've measured the bond strength and we've measured the bond length, you can see that indeed this is true. The high bond strength is associated with the high bond order, followed by the 2.5s being next in line. Now they don't agree exactly, and that has to do with the fact that they're the splitting diagrams are a little different, but they do fit in order of high to low. And then you can say, okay, well, I do know this, that my N2 is going to be higher energy than these are from each other. And then the O2, which is the lowest bond order, is going to be the weakest. And that indeed holds. Very interesting, though, when you look at the bond length, it's almost exactly the same. Whereas the stronger bond is a little shorter, and then the weakest bond is the longest of the 3 bonds, or 3 types of bond orders. And this all bears out, and that's it for molecular orbital theory. So again, understand what molecular orbital theory is, be able to apply key properties to a simple molecules, and again, we're limited to, they're diatomics and they're the same atom, and then you can have them as cationic or anionic. You can even add an electron on. Understand what bonding and anti-bonding orbitals are. Bonding leads to bonding, to bond order. Anti-bonding subtracts from bonding order. Know how to find the bond order in molecular orbital systems. Bonding minus anti-bonding cut in half. That's the rule or the formula. You can create splitting diagrams yourself for S-only systems. Systems with S and P together will be given to you. You'll be given the splitting pattern. Then once you have the bond order, know how bond order, length, strength, and rotation correlate with the models discussed in this unit. Okay, I hope this helps. Work hard.